Hi, I'm Brian Kim. I'm the Director of Engineering for the Pressure Products Company. This video is the third of three segments about risk parameters that one needs to consider before specifying a side window. The previous two segments dealt with the pressure issues and chemical corrosion. This segment is going to discuss the importance of specific failure scenarios for your process. A lot of commercially available sight glasses are rated for 450 Fahrenheit at 150 psi. Side windows' pressure safety margins are rated and tested at their maximum service temperature. So for a side window rated for 450 Fahrenheit and 150 psi with a pressure safety factor of 4, that kind of a thing would be tested at 450 Fahrenheit at 600 psi. The usual rule is that at the max pressure, 600 psi, the side window may leak, but it must not burst. Now that sounds good until you think about it a little. The important issue here is that for this specification, the temperature is not required to rise above the unit's rating. In other words, there is absolutely no margin of safety on the temperature scale. Window materials turn to goo very quickly if you exceed their rated service temperatures. Think about that. There is absolutely no margin of safety on the temperature scale. Now, that total absence of safety margin on the temperature scale is generally okay for liquid processes. Pressurizing liquids to 150 psi is hardly going to raise its temperature. In fact, pressurizing even to 600 psi will raise the temperature very modestly. Also, if the fluid pressure and temperatures are truly decoupled, not having temperature margin of safety would be okay. So if you have a process involving very high temperature liquids, like motor oil, and you pressurize that to 150 psi and heat to 450 Fahrenheit in separate steps, a commercially available side window with those ratings will be fine. In fact, this is how side windows are generally tested. On the other hand, very few actual sight glasses are used with very high temperature liquids like that. Let's use a little common sense here. Most processes that see 450 Fahrenheit involve substances that have much higher vapor pressures than high temperature oils. So the process fluid is a pressurized gas. For water or water-based liquids, the vapor pressure at this temperature is over 400 psi. If you're operating at a 150 psi process and 450 Fahrenheit, you have steam. And of course, lots of processes use compressed gases at these conditions. If your process involves high pressure and high temperature gases, you have to consider the two parameters together. The two industrial units that impart enthalpy to fluids are compressors and boilers. In both of these cases, the temperature and pressure of the exit stream are coupled to each other. You cannot raise the pressure without simultaneously raising temperature deterministically. So, if you have one of these processes and you decide that you need a pressure safety factor, you also need to explicitly calculate where the temperature is going. In other words, if your enthalpy gain device somehow creates a pressure spike that lasts more than a few seconds, you will also be seeing a corresponding temperature spike. And as I said already, side windows are specified with no safety margins on temperature. So you have to explicitly account for the temperature changes and make sure to specify a unit that can accommodate the corresponding temperature rise. Let me give an example. For whatever reason, you decided that a pressure spike is possible, and you want to specify a side window with a margin of safety on the pressure scale. By the way, compression is an expensive operation, so for an industrial process, a designer would try to match, rather than oversize, a compressor to his given application. Now, on a small scale, experimental setups or pilot plants, oversized compressors would be pretty common. For this example, let's say that I have a process pressurized by an air compressor operating at 7 atmospheres, and somewhat randomly I decided that a pressure spike is possible, so I want to specify all components with a margin of safety in order to cover that pressure spike scenario. Sadly, I'm lazy and decide not to bother thinking much about pressure-temperature relations and decide to specify a DIN 7079 fused sight glass. I've been told by various vendors that these things are very strong, so instead of doing the math, I'm just going to rely on the claims of mechanical strength for quote-unquote safety. And their maximum temperature is 280 C, which is my process temperature right here, so that's no problem. And I specify a piece that's going to take 10 times the rated pressure at 280 C, and that seems like a large number, so without doing the math, I decide that the factor of 10 is enough and everything is fine. Of course, I'm being facetious here, but I do believe that more than a few side windows have been specified through just such a decision-making paradigm, or based on some vendor's assurances that their product is quote-unquote just safer. In real life, I would do a little bit of math to develop specifications like this. Now, I have written that down, or some of that down on this slide right here, so that you could check my arithmetic. Typically, when you're thinking about gas compressors, you usually match the required compressor shaft power by using an enthalpy relation, which is not shown here. Then you couple that with pressure ratios using an equation that looks like this, okay, which is a simple modified isentropic pressure-temperature relation. The T's and P's here, these P's and T's, they denote the temperatures and pressures, and the subscripts E's and I's denote inlet and exit conditions. The gamma here is the ratio of constant pressure heat capacity to constant volume heat capacity, which tends to be about 1.4 for lots of common diatomic gases like air. And eta here is a fudge factor that accounts for the entropic losses for the compressor. Here we have a table with some of the values from these equations. You have a process in which a compressor supplies air at about 7 atmospheres, as shown here, which is a pretty pedestrian value. And at that exit pressure, starting with room temperature about here, okay, your exit temperature would be 280 C, which is hunky-dory for our site class that we've chosen. Okay, and as long as this temperature is not exceeded, DIN 7079 site glass can take a lot more pressure. But in this case, if the pressure rises, the temperature will rise also. This first line is our normal operation, and the discharge temperature is 280 C, which is just fine for our DIN 7079 site glass. It'll take this forever. Okay. The next line represents the maximum permitted surge limit, which is 300 C, and that's arrived at a mere 10% spike, not a factor of 10 spike, but a 10% spike in pressure. Okay. At 350 C, which represents only a 1.5 factor pressure spike, okay, your glass will probably not blow out for a short while, but you can't stay here very long. And here, at 480 C, which represents only a 2.6 factor pressure spike, you're going to have serious problems. At this pressure level of 3.6, so this is 3.6 times the initial rated process pressure, the temperature is at the annealing temperature of the borosilicate glass specified in DIN 7079, and at this temperature, the borosilicate glass has no capacity to sustain a mechanical load of any kind, so it's unable to hold any pressure at all. Okay? And obviously, that's a catastrophic failure waiting to happen, and waiting to happen pretty quickly. And that's the point. The pressure rises here that you see are relatively modest and well within specifications of just about any site glass that's available, but that pressure rise is always accompanied by a much more destructive temperature rise. By contrast, fused quartz glass can serve indefinitely at this temperature. So you can comfortably take this to a 3.34 safety factor, okay? And this is really usable. You can spike pressure up to this level and hold it there forever, and the glass will survive indefinitely. So in this example, where pressure and temperature rises are coupled, the soft fused quartz window actually gave a much larger real margin of safety than the normally tough DIN 7079 window. And that's the point that I'm trying to make. Concept of safety cannot be divorced from the process failure scenario you have at hand. In many other scenarios, the DIN 7079 window will provide larger margins of safety. But here, the soft fused quartz glass provides a much larger margin because the scenario is temperature limited. The main take-home lesson I want you to remember is that safety is inherently related to your specific failure scenarios. This scenario I just presented to you is not an exact scenario. We were just compressing air. You may have heard that glass is a liquid in very slow motion. When glass is heated even a little bit above its maximum surface temperature, this very slow motion becomes considerably faster, and the glass will deform permanently. If you are not aware of this kind of behavior of glass, you might think to yourself, well, if this site window can take 280 C forever, surely it'll take a little pressure spike. You should never think that way. In a compressor scenario, pressure spikes come with temperature spikes and glass will deform. This is our DIN 7079 compliant fused glass product. A lot of vendors, including us, advertise as being stronger than other sight glasses and therefore safer. This is our conventional product, and it's capable of taking high temperature glass lenses. These high temperature glasses tend to be soft with low tensile strength numbers, so we do not normally advertise them as being strong. However, in this scenario, where the risk factor was temperature, this conventional product with a soft high temperature glass offers a much larger rear margin of safety. Fortunately, these types of failures are extremely rare, but that's because engineers who design such processes are acutely aware of what I just described, so they build in redundant safeties so that the pressure and temperature risks are essentially non-existent. Of course, if the risk of pressure spike does not exist, what safety advantage is there in specifying a side window with a pressure safety margin? You're better off saving your money for some other way that will mitigate a risk factor that actually exists. As in every other area of engineering, sight glass window design is a combination of trade-offs, and there is no design that addresses every risk factor. There is nothing that's quote-unquote just better. So when you specify side windows, think about the causes for pressure spikes, why your process is pressurized, and what your risk factors are. If you get your side windows from us, our sales engineers are supposed to ask about these, but ultimately, it's your process, and you'll be stuck with the product. So you want to make sure that you understand those risk factors quantitatively, and that you specify your side windows with respect to those risk factors. That's it. This is Brian Kim for the Pressure Products Company. Thank you for watching.